All right, so let's look at an example of how we might use normal distributions in real applications. So let's consider this idea of body temperatures. All right, now here's what we know about body temperatures. We know that they're normally distributed, all right, and they have a mean of 98.2 degrees. All right, so we know that, through tons and tons of historical data. We also know that their standard deviation is 0.62 degrees. Again, through historical data. So we know those facts. So the question we might have is this. Suppose that, so obviously people are going to vary back and forth between, not everybody's going to be right at 98.2. Some are going to be higher than, and some are going to be lower. But let's try to answer this question. If we select somebody at random, what is the probability that their temp is greater than 1.4 or 100.4? So in notation, it would look like this. The probability that the x value is greater than 1.04. Now, we asked in the past that in our previous section, we were asking about probabilities of getting z-scores greater than or less than a certain value. And so the notation looked like this. But the game is still the same, right? What we do is we have our normal curve for temperatures, right? With the mean sitting right in the middle, 98.2. And then we put in our boundary that we're interested in. And in this case, it's 100.4, so it's going to be up here. And we want to know the probability of being greater than that. So we're trying to find this area. So it's simply finding the area under a normal curve, just like we've already done. So the first thing we're going to do is we're going to find the z-score. All right? So find the z-score of the boundary. So convert the boundary to its z-score. And we have our formula for that. Z equals x minus the mean over sigma, right? So in this case, the boundary is x, 100.4, minus the mean over sigma, which is 0.62. And we want to figure out what that is. And that'll be the z-score. That'll be the z-score of the boundary. Okay, so we convert it to a z-score. And the reason we convert it to a z-score is so that we can use our table, right? Because our table A2, is only written in terms of z-scores, right? So this turns out to be 3.54 or 3.55. We're around to 2 decimals, all right? Now, if we look in our table, we will see that, again, our table only gives left areas, right? So our table's only given the area over here. If I look up this z-score, 3.55, I notice I don't have, the table only goes up to 3.50 and up. And what it says is, if you're above 3.5 and 0 and up, the area is 0.9999. Okay, that's the left area. That means this area is 1 minus that, so 0.0001. Very, very small. So the probability of randomly selecting somebody whose temperature is greater than 104 or 100.4 is 0.0001. Now, of course, we could throw this into our calculator, right, using the cumulative CDF. We would do something like this, right? Standard normal. I think it's normal, right? Normal CDF. The left boundary is 100.4, comma. The right boundary is, say, 1,000, comma 0, comma 1. And that should spit out something approximately equal to 0.001 or 0.1. And so all we're doing in this section is we're finding more areas under bell curves. Okay? We'll have a boundary. We want to find an area. All we have to do is convert the boundary to its z-score, and then we can start using our table.